Ruth Bloom. Ruth is going to talk to us for about 45 minutes, after which she'll be happy to answer any questions from the audience. And then we'll ask the audience to step outside for a bit while the committee has some time to talk to Ruth. And then I think hopefully afterwards there'll be some refreshments, right, everyone?
Yes.
Yeah. All right. Ruth.
Okay.
It's a while.
Well, thank you all for coming. My name is Ruth, and I'm going to be talking about some of the experiments that I did for my PhD work. Most of this was also in collaboration with Ming-Wang and Tai Kumbi, who are actually in this room right now. So, first of all, this is an ultra-cold atom experiment, as you probably know. And ultra-cold atoms are just a playground for exploring quantum physics. And one of the main reasons why is because they're so easy to control. So the basic setup for the experiment is we have a vacuum chamber with a dilute puff of gas in it, and we manipulate these atoms into really, really low temperatures where the wave functions overlap and quantum mechanics plays out on a large scale. And it seems kind of esoteric, you know, it's a puff of gas in a vacuum chamber. It's hard to believe that it's relevant to the rest of the world that we live in. But the main property of these gases that makes them so interesting for studying general quantum phenomena is universality, which is basically this idea that different strongly interacting quantum systems imitate each other. And so, you know, experiments that are performed with cold atoms in a quantum gas can be used to mimic the behavior of electrons in solids, of neutrons in a neutron star, you know, superconductors, nuclear matter, etc. Or at least that's what we tell our funding agencies. But this property relies on interactions being very strong, which instead of relying on the fine-tuning of nature, we rely on an experimental tunability that occurs near Feshbach resonances, which are just one of our favorite tools in the field. And with Feshbach resonances, basically what you have is a bound molecular state, which is very weakly bound, and two free atoms which have energy that varies differently with magnetic field. And if you vary the magnetic field to a place where those energies should cross, then you see a lot of really interesting phenomena, one of which is that the interaction strength becomes a strong function of magnetic field, and then you can control the interactions and access universal behavior, which is really great. So these are all very standard techniques in the cold atom community at this point, I would say, and it's kind of emerged, you know, after years of having access to these things, that the vast majority of the experiments observing universal behavior have occurred in fermions, and that's because fermions are protected against certain kinds of side effects that occur when you tune the scattering length to a very large value, or the interaction strength is parameterized by this thing we call the scattering length, which is just a kind of the size that the atoms perceive each other to be. You tune this to a very large value near a Feshbach resonance, and all kinds of processes happen which can deplete the atoms from the sample and cause it to not live very long in equilibrium. So fermions are protected against this, which is why they're so well studied. But there's a lot of interesting phenomena that are predicted for Bose gases and Bose Fermi mixtures, which have to deal with these kind of bad collisions. And so, the Feshbach resonance that we use in our experiments, we're interested in studying a mixture of rubidium atoms and potassium atoms. So the rubidium atoms are a boson, potassium atoms are a fermion. And we vary the interactions between them using this Feshbach resonance, which varies the scattering length shown here. It's a fairly nice broad Feshbach resonance centered at 546 Gauss, which is about 1,000 times the Earth's magnetic field. So we use this resonance, and in addition to the motivation of better understanding these inelastic collisions that limit our experiments, we're also very interested in the mechanisms that control the collisions themselves. So there's a whole body of U-body theory that is focused on the physics of what happens when all the pairwise interactions are strongly enhanced, what happens to the three-way interactions, four-way interactions, etc. And in general, this is a really hard problem, but there's a really interesting solution for strongly interacting quantum particles that was actually conceived in the 70s called the Efimov effect. And whenever you have really for certain resonantly enhanced pairwise interactions, you get these crazy three-body states. So one of their really interesting properties is that this three-body bound state can exist even when there's no two-body bound state. So people like to draw an analogy between this and Baronian rings. So if you look at these rings carefully, if I picked the right one, no single pair of rings is linked together, but if you were to pull on any one of these rings, they wouldn't come apart. And this kind of bounce state is something that has kind of been a mathematical curiosity for a long time. They're also really interesting because they have this sort of fractal structure in the sense where if one bounce state exists, then another one exists, which is a factor of, say, 23 larger, and another one 23 larger than that, and another one 23 larger than that. So the bounce spectrum is a discrete scale invariant system, which is really interesting. So those are the kind of things I'm going to be talking about today. Basically, two-body interactions and their consequences in a Bose-Fermi mixture as measured by the dynamics of a sample of potassium and rubidium atoms. And none of this is possible without actually making the quantum gases in the first place. So I'm going to, for the rest of the talk, basically start by introducing the machine that we use in order to make these samples. And then I'm going to move on to talking about the pairwise interactions between the atoms, which creates a two-body molecular state. And then from there, I'm going to move on to these three-body states that are so important for inelastic collisions. And then finally, we can hopefully have cake. So the structure of our experiment schematically is as follows. So our method of imaging the atoms is destructive, which means that for every data point we take, we prepare a new sample of atoms in order to run the experiment on. So all of this takes place in a self-contained vacuum system. So we've got this, we start with what is kind of I guess a Gilla standard technology at this point. We have a combined vapor cell of rubidium atoms and potassium atoms, which are here in the relatively high pressure area that we call the collection cell. And all this is inside of a glass and steel chamber. And then we collect these atoms here, and we cool them, and then we move them to the other end of the chamber using a magnet that's on a physical translation stage, which is actually really dramatic to see in person. It's quite loud. So this magnet moves and pulls the atomic gas to the other side of the chamber, and in the science cell now, where we have a much lower pressure and also better access for lasers and stuff like that, we actually perform our experiment on that end. But as anyone who's seen one of our lab's notes, that's not the whole story. So here is a piece of my lab in person. And this part of it that I showed you in the schematic diagram is just the coils are right here. This is where the atoms are collected. And then we move the atoms to the other end like that, and the translation is about 1 meter. And here we have, these are all for generating various magnetic fields, various lasers, and these are the cameras that take the pictures of our experiment. So in practice, it's not as simple and elegant as the rest of the slides are. And we leverage sort of standard VEC techniques in our lab, but in order to reach ultra-cold temperatures, we basically have a gas of rubidium and potassium atoms, which are overlapped for the entire cooling sequence. And the potassium atoms are spin polarized fermions, so they're sort of just along for the ride. And the rubidium does most of the work. So we start with a gas of potassium and rubidium atoms in this vapor cell, which is at room temperature, or a little bit hotter, so that's about 300 Kelvin. We do a dual species mop where the clouds are overlapped. The lasers for these two atoms are actually about the same color, so all the optics are just overlapped with each other, which is really convenient. This gets us down to about 1 millikelvin above absolute zero, which is cold. And then we do this transfer to the other end of the chamber, at which point we're able to selectively eject the hottest atoms from the trap. And all that's left are the ones with the lowest kinetic energy. We have a cold sample. And finally, we transfer this into the focus of a laser beam, which holds the atoms. And we further evaporate to a few hundred nanokelvin. So a lot of experiments at this point would keep evaporating. They would go and make a degenerate Fermi gas or a Bose-Einstein condensate. But because the behavior of fermions and bosons is so different at zero temperature, we actually keep the gas at a really hot temperature of about 300 nanokelvin or so that we're above the VEC transition and the two gases are well overlapped. So we have a ultra cold but not quantum degenerate gas at the end of this. And so far, we've taken about 1.5 minutes to do all these things. And then finally, we have our data taking is very simple. It's just a standard absorption imaging. And we illuminate the atoms with a resonant laser light. We cast a shadow onto a CCD camera. We use some kind of state-of-the-art computer to perform analysis. And Then we have, from these pictures, we extract all the bulk thermodynamic properties of the gas: number, temperature, density, quantum degeneracy, things like that. And the idea basically is just to see how did the atoms respond to whatever experiment we did. And at this point in the process of taking these pictures, we actually scatter so many photons that we sort of boil the atoms away, and we have to make a new sample. And that's the life cycle of our experiment. One of the big pieces of this experiment that changed during my PhD is the magnetic trap, which is responsible for this forced RF evaporative cooling. And the idea, so there was sort of a catastrophic failure involving some lightning of the old trap. It was pretty bad. And there were also, it was built a long time ago, and there were a lot of things that we wanted to change. Newer experiments use a lot more lasers, so we wanted all the holes in it to be bigger so we could shoot more lasers through them, things like that. We also wanted the system to be a lot more robust and to not fail with lightning again. Ty Cumbie built the coils, and I implemented the system that controls the hundreds of amps that flow through them to get the two modes of operation that we need. So one mode of operation is just all of these coils turn on at the same time in the directions indicated, and this creates a magnetic field minimum at the center, and it's kind of being held in a harmonic potential. But then if we just turn these coils on, we also have a really good control over the magnetic Feshbach resonance that is key to the results once the atoms are cold. So this was just kind of a electrical engineering project, I guess. We ended up, in order to get these two modes of operation working, we had like two paths. One that just makes the Feshbach resonance field, and the other one with all the other coils. And each one's controlled by a giant transistor, and we can vary the current in each one independently. And then finally we have, this is what the trap looks like in person, installed in our experiment. These are those bias coils for the Feshbach resonance. The atoms are in here. And this is our imaging system, held in a plastic lens tube so that we don't have magnetic field eddy currents running through the metal. And this system has worked pretty well for us. It's totally up and running, and it's great. So we have significantly reduced RF interference on our system compared to before. We have long Rabi oscillations on field-sensitive transitions, and in general, this is an important piece for a lot of the data that we take. So for the rest of this talk, I'm going to actually show the data that we take with all this machinery. So starting with the pairing of two atoms into molecules. So ultra-cold polar molecule experiment is a really popular experiment at JILA. But cold molecules have been present in atomic gases for many years before they got started. And the basic idea is that near a Feshbach, one way to make ultra-cold molecules is to start with a gas of ultra-cold atoms near a Feshbach resonance. And you basically, like, as a function of magnetic field here near the resonance and energy here, when the magnetic field is above our resonance, there's no two-body bound state. And then then at the resonance, this state has zero energy, and then below the resonance, it has some finite binding energy in the order of kilohertz or megahertz. And so we just sweep the magnetic field across these resonances, and the atoms just kind of follow this state, and they go from free atoms into a bound molecule with hopefully the same temperature as the atoms it came from. And so this has been studied pretty widely in gases that make bosonic molecules. So like, for example, the BC-BCS crossover, this was kind of an instrumental thing for studying fermions paired into a bosonic molecule. But the fermionic molecules, like the ones we formed, are less well understood. Even though they have this enormous practical application, which is that they are the first stage in experiments that seek to make degenerate Fermi gases of polar molecules. Now, if those experiments could start with a larger, denser sample of molecules, they're really on the cusp of being able to revolutionize the types of interactions we can model in our experiments. And so this is an important thing to understand. So from a fundamental standpoint and kind of an applied standpoint, this is useful for some definitions of applied. But anyways, the more detailed sequence for creating a molecule looks like this for us, following, standing on the shoulders of other people who have made Feshbach molecules. We start above the Feshbach resonance with just some ultra-cold atoms, and we ramp the magnetic field through the resonance, and then we remove the unpaired atoms, and then we image the molecules on the transition that's usually used to image the atoms. And since all the unpaired atoms are invisible now, we we just see a picture of the molecules. And so this is actually a picture of ultra-cold molecules trapped in a laser beam produced by this method. And then key to understanding how this formation process is the actual rate at which you jump through the resonance. Because we're sort of asking the atoms to follow along into this molecule state as we ramp through the resonance. So if we ramp too fast, they can't keep up and change their state. But if we ramp slowly enough compared to the scale set by the Feshbach resonance, then the molecule production saturates, follows this equation. And so we can kind of separate the physics into two regimes of behavior in this molecule formation process. So we have the fast sweep regime, which is basically where very few molecules are made, and you can sort of just consider this a two-body problem. And then there's the slow sweep regime, where the molecule number saturates, and this is kind of more of a many-body problem. And one of the big motivations behind this research was the fact that typically for experiments, we see that this saturation doesn't happen at 100% of the possible molecule pairs that can be formed. It happens at like 10% or 15% or something very low. And this is quite different from the case for bosonic molecules, where people have associated almost all of their atoms in the molecules. So here's our molecule formation curve. And we're able to actually quantitatively describe the formation of molecules in this fast limit by kind of just drawing a line through this curve and just essentially predicting the initial slope of this line at infinitely fast sweeps. So this molecule creation rate can just be built up from a Landau-Wiener approximation. Basically, you can calculate the probability of pairing two atoms in a box into a molecule, integrate this over the density distribution, and make an exact prediction using only known parameters of the Feshbach resonance, as well as the density of the gas. And this is kind of a nice check, because we're going to go into studying the system where we make fewer molecules than we expect, right? So we want to make sure that we have some quantitative understanding of how many molecules are we making, how dense is our gas, what do we expect to make. So this line has no free parameters, and we see that the molecule creation rate over a variety of density conditions follows this model extremely well. And so from this we say, okay, we have a good understanding of how to image and create molecules, which unfortunately does not lead to the creation of a lot of molecules, but we understand it. So this is the saturated regime, the many-body regime of the curve now, where we can't apply a simple back-of-the-envelope calculation to predict how the molecules are going to form. And the reason why is because once two atoms form into a molecule, they're paired, and then they can't pair into another molecule. So you see a depletion of the gas in such a way that there's a limited number of pairs that can form. And so we actually have to consider this when we have the saturated limit. Anyways, so the molecule formation here, when we collected data over a huge variety of conditions, and under these conditions, the parameter which seemed to most predict what fraction of the atoms would turn into molecules was the degeneracy of the potassium atoms. So we plot, for a variety of ratio of potassium and rubidium numbers, we plot the fraction of atoms that are formed into molecules versus T over Tf. And the higher the temperature goes, the lower the formation efficiency is. And you can sort of see that qualitative trend by just imagining that the two atoms are only going to form into this molecule at temperature if they have very similar momenta and positions already. So that the hotter the temperature of the gas is, the more chaos there is in the different momenta and positions, and the less likely it is to find pairs of atoms that are close enough together and moving together in a way that they would want to make a molecule. Yeah?
Is this just fraction with respect to rubidium?
It's fractional with respect to the minority species, which I think is rubidium for all this data. Yeah. So it's fraction of what's possible. Yeah. So we wanted to study this all in the thermal limit, where there's no BEC, because the density overlap between the gases is better. And so we vary the number ratio as we go to lower temperature because we want to avoid Bose-Einstein condensate. In any case, we found this dependence, and we wanted to see whether a kind of conventional model for understanding molecule formation was going to work for this system. So for the formation of molecules from two bosons or two fermions, there's actually a fairly simple calculation you can do to predict how many molecules are going to form in this limit. And what you basically do is you take Monte Carlo distribution, you generate like an example quantum distribution of initial atoms. And then you kind of just pull atoms out and try to pair them with each other based on how far apart they are in phase space. And once two atoms pair, they're removed from consideration and you try to pair the other atoms. So this simple model has worked really well for bosons, two bosons or two fermions pairing. But what we find is a very striking deviation from this model for our system, which kind of implies that this phenomenological understanding of how pairing works in a Bose-Fermi mixture is actually not adequate. So what we have here at the 0 dash line is basically what this model predicts. And in high temperatures, where the quantum statistics are kind of irrelevant, we see good agreement with the model. In fact, we even fit this model to sort of extract what this phase space distance should be between the atoms, and we find that it's consistent with measurements in other mixtures. But then as we go to lower T over TF, we see a dramatic reduction in the molecule. So basically, if you were to look at this plot with the way it's predicted to be, a lot of molecules are predicted to be produced. But then, in fact, we're just consistently coming in below the mark. And we're pretty sure we're counting all of them. We've very specially prepared these gases under conditions where the density is very low. And we don't expect anything else to be interfering with the process. And so the only really thing that's different about this system compared to other systems where this process is well understood is that the molecules are fermions. And so it's hard to believe that this isn't a consequence of those statistics. And it kind of opens the door to maybe some more detailed theoretical calculations of how this pairing works. But it also serves as a guide that whereas this model says you do a lot better by going colder, and it's a lot of work to go colder, it might not actually be worth it if your goal is to just form a ton of molecules. And because the motivation for these studies was to study, how hard is it to make a degenerate Fermi gas of molecules anyways, we also studied the temperature of these molecules. And this actually turned out to be kind of a more interesting story. There's not as clear an explanation as to why the quantum statistics of the molecules would affect their temperature. They're not quantum degenerate. They're a T over TF of 1 or so. But what we find is that over, here's an example of how we measure the temperature. So if we have the atoms confined in a tight trap and we release the trap, and there's some RMS velocity of the atoms, the cloud just expands with that velocity that's set by the kinetic energy. So if we measure the cloud size as a function of time, we have a measure of kinetic energy. And the rubidium, because the clouds are in thermal equilibrium, they should have the same temperature, and but they have different masses, so they expand at different rates. So here's the rubidium atoms expanding in the red dots, and the potassium atoms expanding in the blue triangles. And then based on the measured expansion energy of the rubidium, you would expect the molecules to expand this quickly. But they don't. They actually expand much more quickly than expected. And it corresponds to a temperature which is about 1.4 or 1.5 times higher than we would have expected. And so we were like, we did a lot of systematic checks to see if this was kind of a weird thing, but then later when we went back and searched the literature, it's actually every documented case of a measured molecule temperature with fermionic molecules has had this kind of a factor in it, where the molecules are formed much hotter than the gas they come from. We're not the first ones to observe this. So we decided that maybe there was something weird going on because we were doing magneto association. So remember I said that we form the molecules by ramping the magnetic field through this resonance where interactions become infinitely strong and there's quantum phase transitions and all kinds of crazy stuff going on. So maybe that's just like a bad regime. Maybe something weird happens there. But there's other ways to make molecules. So we can also make a molecule by bringing the magnetic field to a place where a molecule state has a low binding energy and using an RF pulse to spin flip potassium atoms into the molecule state directly. And if we do this, we create a similar number of molecules compared to when we do magneto association. And here's an example line shape. So here's the bare potassium transition that just flips potassium atoms from one state to another. And we're using the -7/2 to -9/2 transition. And here the -9/2 are the only ones that are visible to our imaging light. So here's like an RF pulse that just moves potassium atoms. And then here's if you detune the RF pulse by in an energy equivalent to the binding energy of a molecule state, you see another peak here. And this peak is the formation of molecules. And the difference between these two peaks is their binding energy. So we tuned up this RF association process, And we find that the temperature is the same between the two different gases. What I'm showing here now is for all of the data where we measured the molecule number for all that calculations, we also measured the temperature. So these black points are all that same data plotted versus the T over TF of the potassium atoms. And then these are new data with RF association measuring the temperature also by expansion velocity. And we were like, oh look, there's a little bit of a trend upwards with low T over TF. And so I plotted here, just using Brian DeMarco's thesis, the expected kinetic energy of the potassium atoms for these T over TFs. And it's not nearly enough to explain this extra difference. And the rubidium atoms we kind of use as a thermometer, so the rubidium atoms are just at this horizontal line of 1. So basically what we see is that over a huge range of conditions, this is true. So like in these previous references where they had measured this high temperature, there was like, oh, but our gas is a little bit quantum degenerate, or we have a high density, so maybe there's some loss or something like that. But it's clearly not an issue of degeneracy, and it's also clearly not an issue of inelastic loss, because we have these. If we plot versus the initial density of rubidium atoms, we see that this effect is quite consistent, even in the limit of. Even if you extrapolate to zero density or extrapolate this data at infinite temperature, we definitely see this strong effect. And out of the crippling self-doubt that we might have dropped a factor of 2 somewhere, we ran these calculations a lot of times. So this data is actually, someone find it, but it's, so we actually haven't published this data yet because we don't have a clear understanding of why this is happening. But one thing we do know is that our expectations of the energy and the way this formation process works is based on a 2-body picture. But what we actually know now is that the physics of the system near Feshbach resonance is not really a 2-body system. There's strong interactions between molecules and atoms and other things like that. And so this kind of led us to some of this like peculiarity sort of motivates maybe taking a deeper look at a less simplified picture of how the interactions work in our system. So in the last section I kind of explained our efforts to make a degenerate Fermi gas of molecules, which we got to T over TF of about 0.9, but I don't think that really counts. But I think the physics of why that couldn't happen is actually really interesting. And then now we're going to move on to talk about 3-body collisions in the gas. So 3-body physics is really kind of actually an old problem. So if you've taken a mechanics class, you know that solving like 2 particles interacting gravitationally is really easy. But the problem of how 3 particles interact is already actually generally impossible. Even in classical physics, there's just more equations than there are variables, and in many situations the system acts chaotic. And then you see a lot of cool situations come out in classical physics too. So, for example, I think my favorite classical 3-body system has got to be the asteroid belts. In the solar system, you can't really see it here. So if you have the sun and you have Jupiter, and you have some asteroids, the asteroid and the sun and Jupiter form a 3-body system. And one of the solutions to this problem is that the asteroids actually orbit around the Lagrange points in empty space. So you actually have these asteroid belts that are orbiting nothing, that are in the empty space, that are like in a triangle with Jupiter and the sun. And you can see that. That's awesome. There's also kind of this topological thing I alluded to before with the Bromian rings, where no single pair is linked, but the 3 hold together. And this was actually used, amongst other places, as the coat of arms in a really powerful Italian family. So this is etched in marble in some sort of giant palace that they owned, I think. So this idea has been around for a while. And this is actually related to the 3-body states that we study in our mixture. More recently, people have been really interested in the 3-body physics for nuclear physics, actually. So in the 1970s, it was predicted that there could be these nuclear bound states in which have this gigantic spatial extent and these exotic scattering properties. And one of these properties would be that they're extremely large. And people have managed to take data now where they make these exotic nuclei. So this is the lithium-olevian nucleus. If you can't see it down there, it's a 3-body bound state between a lithium-9 nucleus and 2 neutrons that are orbiting it. And it's as large as a lead nucleus, even though a lead obviously has a lot more in it. So it's large in a way that violates the rules of classical mechanics, and these 3-body bound states in nuclear physics are a fundamentally interesting object. And they're all, weirdly enough, despite those totally different energy scales, thanks to universality, these same systems also control the dynamics of many atomic systems near Feshbach resonances. So the basic scenario that makes this three-body solution available, it's one of the only examples I can think of where quantum mechanics is actually presenting a simpler solution than classical mechanics. But yeah, so you have this system in a Feshbach resonance. So here's the energy, here's one of the scattering links. So here's the Feshbach molecule state we're familiar with. It has zero energy at the Feshbach resonance. But if we look at the state of three atoms, there's this infinite series of bound states. So every time you rescale the scattering length by a factor of something, you see the same sequence repeat over again. And when the scattering length is tuned to infinity, there's an infinite series of ever increasingly large bound states. And this remained an esoteric prediction of theoretical physics for about 40 years until some people in a cold atom system were actually able to measure signatures of these states near Feshbach resonance. And the way these states work is, it's because they're so weakly bound, they're very difficult to measure directly, but we can see their echoes. So we can see, for example, if the energy of a three-body trimer state is degenerate with the energy of three free atoms in a place like this, you see a huge enhancement in three-body loss in the atoms. And so if you plot the atom loss as a function of scattering length, you can actually reveal the spectrum of FMOF states. And depending on the masses and stuff like that of the constituent particles, this scaling factor lambda that sets the discrete scale invariance can be anywhere from 2 to 2 million, I guess, or probably infinity for particles that exist in nature. So the density of these states is a strong function of masses. In any case, we're far from the first ones to observe these in ultra-cold atoms. But what makes our system unique is that we're the first ones to really chase this down in a Bose-Fermi mixture. And the types of effects we're looking for are basically these loss resonances that occur when the three-body state has zero binding energy, and these create atom loss. So this process is called three-body recombination. Basically, three atoms come together, they form a deeply bound molecule. All that energy has to go somewhere. It turns into kinetic. So this distributed and equivalent amount of kinetic energy propels the atoms out of the trap, and they disappear. Similarly, and I show this as an explosion, but this energy we're talking about will be like gigahertz or something. It's really small. But all energy scales seem gigantic in our experiments. The other type of FMOF resonance occurs when the three-body state is degenerate with the energy of an atom plus a molecule, and intuitively this creates, instead of atom loss, it creates atom-molecule collisions. And that's what we're going to talk about first. So to study atom-molecule loss, we prepare a gas of atoms and molecules, and we put the magnetic field at the scattering length where we're interested in, and we watch the loss. So here's a gas of atoms and molecules. Here's the atoms, here's the molecules as a function of time. And we can fit this to some differential equations at different magnetic fields and use this to measure a coefficient that describes kind of the probability of having this kind of a collision. These sorts of collisions are also really interesting from a practical perspective because they limit the lifetime of the Feshbach molecules that are interesting to study. And what we find when we plot this all is a very strong resonance in the inelastic collisions. So, and we're pretty sure that it comes from a rubidium, potassium three-body state, because when we prepare a gas of only rubidium atoms and molecules, we see this huge increase in the loss rate as a function at this very specific scattering length. But when we prepare a gas of potassium atoms and molecules, we see these loss rates, which are very, very small. And so that, from that, we're pretty sure we've seen a signal of one of these FMOF states that's formed out of two rubidium atoms and one potassium atom in the system, like this one here. And so this is pretty exciting. Theoretical physics was kind of able to predict that there should be an FMOF state in the system somewhere, but whether it would be within our imaging range was less clear. So the fact that it exists here actually nails down a lot of parameters. But there's another question that's kind of related to that a lot of people are interested in the field, which is can you predict where an FMOF resonance is? It's an interesting test of like the ability to model the atomic potential, but it's also just like, okay, so if I want to have a long-lived sample of molecules, I should probably be holding it at this scattering length or this scattering length, and definitely not this scattering length, because like the loss rate is much higher here, like by a factor of 10 or something. So, you know, that's good information to have, right? But it took a lot of work to make these measurements. It would be really nice if you were designing a new experiment with different atoms, if you could just kind of call up a theorist and be like, so what's a good scattering length to work at? But the absolute and so it's really exciting that in Efimov's theory about this kind of stuff that we're sort of hijacking for atomic physics, they just talk about the spacing between resonances, but not the overall location. But people who measured these things in homonuclear systems, where you have a 3-body state with all the atoms the same, they actually did see this really cool pattern where the Efimov resonance locations were in the same place for all of the systems. So like there's basically one parameter which is essentially the size of the atom, and if you know that parameter for 3 ultracold cesium atoms or something, you can just predict the entire spectrum of loss features. And then what's even more interesting is that if you apply this prediction to, you know, this prediction represents this dashed line here, and then the vertical axis represents the entire possibility of locations for resonances, which were presumed to be randomly distributed before people discovered this. But if you look at like all these really different types of atoms, you always see them lying on this line, the locations, the Efimov resonances. And so some people, some theorists were really excited about this, and they came up with some new models that were able to predict how this came about. And similar models also said, hey, you know, that probably means we can tell you where the Efimov resonances are in heteronuclear systems too. Especially the kind that exist in 3-body recombination, which is a different loss process we haven't measured yet. So heteronuclear systems are more complicated. The 3-body physics of the heteronuclear systems, where you have a mixture of different types of atoms, because you have like, so depending on what the ratio of the masses of the things in the 3-body state are, the density of Efimov states is really different. So like in this lithium-11 nucleus, you would only expect one state every time the length scale of the system is changed by a factor of about 10 to the 18. You're probably not going to see multiple resonances in there. Because I think that even for our Feshbach resonances, we talk a lot about how awesome our tuning range is, and we can tune the scattering length by like, I don't know, a factor of 100 or something. And then, you know, before other length scales interfere. But in nuclear physics, they don't even really have that. They just have to keep making different nuclei until they see one that nature has fine-tuned to have the right interaction strength. And so that is not a favorable scaling at all. So that's why people use ultracold atoms, because when you have 3 atoms with the same mass, every time the scattering length tunes by a factor of 22.7, you see another Efimov resonance. Our system is similar, but a little bit worse. We see an Efimov resonance every factor of 100 in scattering length, which means we may or may not see one. And there's new experiments now with lithium cesium where they see like 1 Efimov resonance every factor of 5 in scattering length, which is a really interesting system. So heteronuclear systems are interesting, and the question is, are they as predictable? And I guess the one last thing to note about this, so if we have the scaling factor of 100, why would we study this in this system? It's because a different potassium-rubidium mixture, potassium-41 and rubidium-87, did see an Efimov resonance that just happened to be in the middle of their tuning range. So we can test this kind of universality of the 3-body parameter, or predictability of the location of Efimov resonances by asking the question, are our resonances in the same place as the one that was observed by somebody else in a very similar but slightly different atomic mixture? And in order to do that, we're going to shift from studying molecule loss to studying atom loss. So atom loss, by 3-body recombination, is measured in the same way, but instead of preparing a gas of atoms and molecules, we just prepare a gas of atoms, and we move the magnetic field near the Feshbach resonance, measure the variation in the number and temperature of atoms as a function of time, and from this we can extract the coefficient that determines the probability of 3-body recombination collisions. And in some sense, you can see this as a measurement of the 3-body correlations in the system. So when we measure them, we, as a function of magnetic field, we see a very dramatic dependence of this loss rate on magnetic field. Notice this is a log scale, and I'm only labeling every other order of magnitude, so this is pretty big. But that's actually expected. That's a well-known property of Feshbach resonances, that loss that loss occurs on here. And then this little resonance off to the side is actually just another little Feshbach resonance. So to quantify the fact that we don't see any features here, I'm going to switch to plotting versus scattered length. So if we saw an Efimov resonance, so if the three-body parameter was the same in our system and in the other potassium rubidium mixture, we would see data falling on this orange curve. And that would basically say, generalizing this pattern that was established for homonuclear systems is just totally smooth. And we can now predict all of the Efimov physics in heteronuclear mixtures, case closed. But obviously that's not true. Our data very much deviates from this line and very nicely follows this line, which is the prediction of the absence of Efimov resonances. And so what this says is that this isn't like disproving Efimov physics. This is just saying our resonances are in a different place. This simple prediction didn't work. So if you go to negative scattering lengths, a prediction based on the universal three-body parameter also predicted that we should see kind of a decrease in the inelastic loss right here due to an interference effect. And this also contradicts our data. And so I think the basic conclusion from this is that the location of these resonances and the prediction of three-body physics is not a straightforward extension of the case where you have three identical atoms at this point. And I haven't been reading the archive too carefully, but I think that's still true. So so basically what we have is we have these measurements that suggest that a more kind of rich landscape of three-body physics exists in these heteronuclear systems, which is just an interesting area to study. And we also have this observation that predicts that we should have very strong atom-molecule interactions in our system because we're near this Efimov resonance that we did measure, and which could in fact be related to our molecule issues that we saw earlier. But in any case, we can rule out Efimov resonances over a broad range of scattering lengths. And in analogy to the previous result, where we put all the homonuclear data on one line to see if it all aligned, all the resonances were all on the same line, this is an analogous plot for all the data that I know of for heteronuclear systems, which is a much smaller amount. So this is that lithium-cesium mixture, this is us, and this is the resonance we were trying to duplicate. And this is the universal prediction that is an extension of the homonuclear case. And anyways, it seems like this is an interesting system, and we understand the KRB system very well now. But I don't know if we can say that we can use it to predict other systems. So yeah, that's our results. Basically, we are doing really detailed surveys of the dynamics and kind of survival of atoms in a quantum gas mixture of rubidium and potassium. And this kind of started by, unfortunately, not moving towards a degenerate Fermi gas molecules, but by uncovering some interesting signatures that could reveal more interesting interactions in our sample. And because we then went on to study three-body interactions, where we found that for most of our conditions, there is a strong atom-molecule interaction component, which might actually imply that these results are not general to most Fermi mixtures, but specific to us. And in the process, we tested some universal theories and got some papers, and that's pretty much it. And in the future, our experiment is actually going to take a really different direction. So we have basically, there's a lot of text on the last slide, so I thought I would just show pictures for this one. So most of the progress in few-body physics in the last couple of years has come from comparing different systems against each other, like cesium versus lithium or something. Our experiment is very specifically set up for potassium rubidium. So we're kind of going to move away from few-body physics in the future, and my lab is already starting to set up some really cool experiments. These are atom clouds, which are being distorted into different shapes by a dynamically variable optical track. And the idea is eventually to duplicate Eric's famous rotating BEC experiments with an optical potential. So that's one really interesting future direction for these things. Another really interesting future direction that I'm very excited about is that we got recently a grant to help collaborate with the people who are going to put a KRB experiment in space, like literally on the International Space Station. So that's another very exciting KRB future event to look forward to. And with that in mind, I'd like to thank everybody I worked with while I was here, and that's my talk. And I know this is an old picture, sorry. Yeah, Sarah?
Would you expect the ethanol resonance to be the same, like if you switch the potassium from like what goes on to fermium? Like I don't know a lot about ethanol.
Well, that was kind of the question we were trying to answer. So there were some predictions that said all it should matter is the ratio of the masses, right? And 87 divided by 40 is really similar to 87 divided by 41. And the sizes of the atoms are pretty much the same. So yeah, so the theories from the systems of identical atoms kind of did lead us to expect that we would see the same exact behavior in the two systems, that switching the isotope of that one atom shouldn't matter. So it was kind of a surprise, I think, when we found that, in fact, the resonances are in a really different place. One thing that's really different between the two systems, though, is the range of universality, I guess. So there's a short-range non-universal potential that's unique to each atom, which is different in the two cases, and it's potentially more relevant in our system due to the strength of the Feshbach resonance, and this might somehow be playing a role. But effectively, all that's really different between the two systems is the isotope of that one potassium atom, and it's surprising that it matters, I think. Yeah. Yeah. Roman?
Is there any physical intuition where the fractal pattern comes from?
Okay, well, I'm about to really get some hate from all the theorists on my committee, but as far as I understand it, yeah, actually, sorry, now that it just comes out of the math. I mean, there's I don't know, John, is there a good way to understand it?
I'm sorry, what was the question?
The discrete scale invariance in FMOD physics is very unusual. What happened? What's going on there?
I have no idea.
Yeah, I mean, you can go through the math, that there's an effective 1 over r squared potential, the three-body problem, and it turns out it's an analytical solution. So in principle, you could work through the math yourself, following Eric Broughton's 100-page paper on the topic. But I would recommend it. But it's cool. It's very unusual. I can't think of any other system. The scale invariance is really common in condensed matter physics, right? But discrete scale invariance is deeply weird and very exotic. Yeah, Ramin?
So in the molecular formation, when you have this Lagrangian process,
Yeah.
you got one example where you were able to get up to 15%.
Yeah.
And you said there was a Monte Carlo prediction for that. What was how often was it?
Let's see. I don't know. So for the low conversion efficiency ones, the prediction's actually pretty much spot on because that's at a higher temperature. It's only the high conversion efficiency ones. And this is one of the reasons. In fact, we weren't the first ones to study molecular formation efficiency in KRP. We were the first ones to study it under conditions where the model predicted a really high efficiency of creation. And this regime of really low T over TF, but still having a thermal opposed gas, was predicted to kind of associate all of the atoms into molecules essentially. So right here, for example, where if you look at this point, we're creating about like 45% of the rubidium atoms into Feshbach molecules. But if you look at this plot, the model predicted about 20% higher than that. The model predicted about 60% of the atoms would be converted into Feshbach molecules. So because of the size of this deviation. But if you look over here, where the effective, at high temperatures, where it's very weak molecular formation, then the model is spot on, actually.
Is that because the model is just two-body problem and you're working with some kind of many-body problem?
Well, I would argue that it's a many-body problem for the other quantum statistics too. So for example, like, you know, in Cindy's experiment, they had this where they were pairing fermions together to make bosonic molecules. And studying that versus T over TF, that low T over TF, that model worked quite well. Whenever you have a saturation effect like this, I think it's a many-body problem in a sense, right? Because the